All right, let's dive right into this explainer on plant mineral nutrition and how it, quite literally, shapes our entire planet. Whether you realize it or not, the exact way plants obtain and use mineral nutrients dictates basically everything, from the food sitting on your plate to the overall health of global ecosystems. So we're going to break down exactly how this all works today, starting way out at the massive agricultural scale, and then zooming all the way down into the cellular biology of a single leaf.
Here is our roadmap for today. We'll start with the global fertilizer impact, move into defining essential elements, look at the macro versus micro classification, do some detective work on deficiencies, and then wrap up with the 4 functional groups. Starting things off with Section 1, Global Fertilizer Impact.
We've got to start by looking at the big picture. High agricultural yields are entirely dependent on mineral fertilizers. In fact, crop yields actually show a direct linear increase with the amount of fertilizer they absorb, particularly those essential nutrients like nitrogen, phosphorus, and potassium. And because of this direct relationship, global consumption has just skyrocketed. To put it in perspective, by 2010, consumption hit an astounding 180 million metric tons per year. We are quite literally feeding the earth just to feed ourselves.
But as you might guess, this massive consumption comes with a pretty steep environmental cost. I mean, we are burning incredible amounts of energy here. Over half of all agricultural energy goes into just producing and distributing nitrogen fertilizers. Meanwhile, our phosphorus production relies on non-renewable resources that are actually projected to peak this century. But honestly, the most shocking part of this whole process is the inefficiency. Plants typically use less than half of what we apply to the soil. The rest? It just leaches away, causing severe nitrate contamination in our drinking water and fundamentally altering global ecosystems through atmospheric nitrogen deposition.
Let's move on to Section 2, Defining Essential Elements.
So, what exactly makes an element essential? Well, the crucial point here is that a plant absolutely must have these specific elements to complete its life cycle. It is a fundamental biological non-negotiable. If you take away an essential element, the plant is going to show severe abnormalities in its growth, development, or reproduction. But if it has access to just these elements, along with some water and sunlight, a plant can actually synthesize every single compound it needs for normal growth.
Which brings us to Section 3, Classifying Plant Nutrients.
When we classify these nutrients, you have to remember that macro means amount, not importance. Right? While plants get essential non-minerals like hydrogen, carbon, and oxygen directly from water and the air, they rely entirely on the soil for their minerals. Plants need large quantities of macronutrients, like nitrogen, which makes up about 1.5% of their dry matter. But get this, they only need tiny, microscopic trace amounts of micronutrients to function perfectly. We're talking iron at 100 parts per million, or molybdenum at just 0.1 parts per million. But missing that tiny fraction of molybdenum is just as devastating to the plant as missing all the nitrogen.
All right, let's jump into Section 4, the detective work of diagnosing deficiencies.
This is where we get to play plant detective. Diagnosing a plant is really all about reading the visual clues on its leaves. And your very first major clue is mobility. Mobile elements like nitrogen, potassium, and phosphorus can easily be moved around inside the plant. So when supplies run low in the soil, the plant selfishly salvages those nutrients from the older, mature leaves to feed its new growth. Because of this, symptoms are going to appear in the older leaves first. On the flip side, immobile elements like boron, iron, and calcium, well, they get stuck where they are. When they run out, the new growth is totally out of luck. So those deficiencies show up in the youngest leaves first.
And finally, Section 5, the 4 functional groups and their deficiencies.
To really decode these deficiencies, we need to categorize the elements by their biochemical day jobs. So Group 1 elements act as the foundational building blocks. Nitrogen and sulfur are assimilated to create the absolute core organic molecules of life. We're talking amino acids, nucleic acids, and proteins.
And this right here is the mobility rule in action. Because they both build proteins, lacking either nitrogen or sulfur causes stunted growth and chlorosis, which is that characteristic yellowing of the leaves. But because highly mobile nitrogen gets pulled from the bottom of the plant, it fades the older leaves first. Sulfur, however, is much less mobile, so that exact same yellowing shows up at the top, fading the younger leaves first instead.
Moving on to Group 2. These elements serve as the plant's energy currency and physical scaffolding. We're looking at phosphorus, silicon, and boron here, and they often form ester linkages right inside the plant.
So if the energy currency of phosphorus is missing, which means a severe lack of ATP, the plant gets really stunted. But interestingly, instead of turning yellow, the leaves turn this unusual dark green, or sometimes even purple, with no chlorosis at all. On the structural side, lacking boron literally ruins cell walls. This causes stems to become brittle, and you'll see this pretty terrifying black necrosis, basically tissue death, in the young leaves and terminal buds.
Next up is group 3. These elements, potassium, calcium, and magnesium, exist as free or bound ions in the plant tissue. They act a lot like cellular traffic cops, regulating osmotic pressure and activating some really crucial enzymes.
As a detective, you'll be able to spot a magnesium deficiency by looking for intervenal chlorosis, that's yellowing specifically between the veins on older leaves. That happens because it's mobile and forms the center of the chlorophyll molecule. A potassium shortage also hits those older leaves first, but it shows up as a mottled or marginal yellowing that eventually turns into dead necrotic spots. Meanwhile, an immobile calcium shortage literally destroys the cell division areas, which kills off the brand new root tips and young leaves entirely.
Finally, group 4 contains the metals essential for transferring electrons. Elements like iron, manganese, copper, nickel, and molybdenum are basically the biological wiring of the plant. They allow for reversible oxidation and reduction during major life reactions like photosynthesis and respiration.
Now, because iron is completely immobile, its deficiency causes intervenal chlorosis in the younger leaves, which is literally the exact opposite of magnesium. In severe cases, the newest leaves can turn completely white. Missing manganese brings small necrotic spots alongside that yellowing. And remember that tiny trace amount of molybdenum we talked about earlier? Well, missing that fraction of a percent can cause this bizarre twisting of the foliage known in some plants as whiptail disease.
To wrap up this explainer, I really want to leave you with a provocative question that connects all this microbiology right back to those macro-environmental impacts we started with. We know exactly what plants need at a cellular level, down to the parts per million, to avoid these devastating deficiencies. Yet our current method to prevent this is just dumping 180 million metric tons of fertilizer globally, heavily polluting our water and air in the process. So how can we optimize this delicate balance to feed the world's growing population without destroying the very ecosystems that support us? Definitely something to think about the next time you see a yellowing leaf.